Hey everyone, today I want to explain the solution to problem 1696 on LeetCode called Jump Game 6. In this problem, we're given a number line and n steps. We are also given a number, say k, which represents the most steps we can take forward in each turn. On the number line are certain numerical values. Every time we land on a number, that amount is the number of points we get. If the value is negative, we lose points. The question is, given this number line and k, what is the highest score we can obtain by the time we reach the last number? At first, the answer may seem obvious, but coming up with an approach that works for all cases is a bit trickier. To start, we can express this number line as a one-dimensional grid. This grid will have a height of 1 and the length is given by the problem. With this, let's try to come up with a procedure of getting the high score. First, we should land on every possible positive value. Positive numbers are always going to increase our score, and it's always possible to land on all the positive numbers. One thing we should take note of is that backtracking is not allowed. This means that if we pass a positive number without landing on it, then it is impossible to go back. With this in mind, if there are multiple positive numbers, then we should always land on the closest one. So far, the strategy is to choose the positive number as our next step, and when multiple positives are present, we choose the closest one. So what happens if there are no positive numbers that we can reach on the next turn? Let's say we have the following number line. K equals 2 and all our options are negative. For now, let's pretend our code only stores numbers that we can land on, and we do not keep track of future values until later. Here, we have to choose between negative 2 and negative 10, and we choose negative 2 because it causes us to lose fewer points. However, the next square is actually negative 100, and now we also have to land on negative 10 to avoid losing 100 points. But in the end, we actually lost more points than necessary. So what if we land on negative 10? Well, the same thing can go wrong. The next square can be positive 100, and we could have just landed on negative 2 and only lost 2 points instead. This tells us that if we started from the beginning of the grid, we cannot have a simple solution. So what if we start at the ending? Along with this change, we will also add a grid where at position x, we store the optimal score we can obtain if we started from that position. In this example, we're going to start at position 9 with a value of 7. In our second grid, we can call it an array, the last value should be 7, since this is the highest score we can get starting at position 9. Now let's move one step backwards. We're now at position 8 and we lose 3 points. But negative 3 is not the high score obtainable from position 8. It's actually 6. The game only ends when we reach the high square 9. So this means that if we take one step forwards, we can actually gain a net total of 7 points. This means that the high score obtainable starting from the square number 8 is 4. Again, we take another step backwards to position 7. Our current value is negative 1. This case is a little different because k equals 2, so we can actually choose between 4 and 7. In our problem, we will always choose the maximum value. If we choose 4, we will gain an additional 4 points by the end of the game. And choosing 7 means we will gain an additional 7 points by the end of the game. As a result, our maximum value here is 6. Let's take one more step. At position 6, our value is positive 4. We can reach up to 2 squares ahead, so 7 is now out of reach. So we must choose between 6 and 4. Since 6 is greater, that's what we go with. So the maximum score we can get at square 6 is 10 points. See where this is going? If we continue until we reach square 1, we essentially have our answer, which is the most points scored if we start from square 1. A solution like this is known as dynamic programming. By using this procedure, we can get that the maximum score is 17. You can pause the video to confirm that this is the answer. To program the solution, we can create an empty array to store the optimal values. But for each square, how do you find the highest value within a reach? For instance, take our current example and say we're at position 3. Since k equals 2, we have to find the greatest element that is up to 2 squares ahead. K is small here, so we can check every value. But as k increases, we have to loop through each value, and this gets increasingly more expensive. For the first approach, we can try using a sorted array which keeps all the values in ascending order. Every time a new value is added, we can use the binary search algorithm, which takes up to log base 2 of L computations, where L is the number of elements or length of the array. With this method, getting the maximum value only takes one computation, and that would be finding the last element of the array. So far, the program runs an n times log base 2 of L computations. And since the most elements in the array is equal to k, the worst case scenario would be log base 2 of k. This is reasonable, but the problem lies not in adding elements, but removing elements. You see, every time we take another step backwards, there's a good chance that a value becomes out of reach. It is difficult to know exactly where this exists in our sorted array, and we usually just loop through all of these values to find it. And doing this would take an extra n computations. We can use a faster method, but this would make the code a lot more complicated, and there's also faster ways to do the same job. In this approach, we store the values in a type of map. A map is where a key is linked with a value. We can use a type of map that sorts the keys in ascending order, and since keys cannot be repeated, we use the value to store the amount of keys present. Here, we have 7 as our value in the array. We store this value in the array as the key, and store 1 as our value in the map because there's only one 7 present. When you take a step down in the grid, we use the highest key in the map and add it to the array. So now we have 4, and that is also added to the map. Eventually, if we repeat this process, there will be a number that we can no longer reach. In this case, it's 7. And instead of searching all the values to remove it, we can just search it by the key, and this only takes up to 1 computation. So this code runs in at most n times log base 2 of k computations, and it's relatively a lot easier to implement, but still not the fastest solution. In our final approach, we store values in a deck. You can think of a deck as a double-sided line, where values can be either removed or added from both ends. For this approach, instead of sorting the maximum value, we store the position of the maximum value. To understand the solution that uses the deck, we have to use an example first. Also keep in mind that k has increased from 2 to 3. Here, we start at position 9, and we add that to the deck. We have to keep track of the positions, not the values. Next up is negative 3 at square number 8. First, we get the position at the head of the deck, 9, to get the highest value that we can reach, 7. And we add 7 to negative 3 and put it in the second array. Then we also add this to the deck. Now we can do the same thing to the next square. We use 9 to get 7 and add it to negative 1 to get 6. And we put position 7 at the end of the deck. Now let's make an observation here. Position 8 has the value of 4, and position 7 has the value of 6. This means that we never choose position 8 whenever position 7 is one of the options. The only reason we would choose position 8 is if position 7 is out of reach. However, position 8 will always be out of reach before position 7 does. This means that position 8 is obsolete when position 7 is always here, so we can just remove it from the deck. Let's keep going with this example. We're now at position 6, and the highest is still position 9. We can use that and get 7 added to 4, and we have 11. Now we add position 6 to the end of the deck. We compare position 6 to position 7 and find out position 6 is higher, so we can remove position 7 from the deck. The same thing goes with position 9. We find out position 6 is greater and we remove it from the deck as well. Let's continue animating the last few steps of this solution. Okay, pause. We notice here that we are at position 1, but now position 5 is out of reach, so we simply just remove it from the deck. Now we can use position 2 to find the optimal score we can obtain from position 1, and that is 20. And that's it, 20 is our solution. If you want, you can pause the video to confirm this. Keep in mind that k increased from 2 to 3. This marks the end of the implementation section. I will show my Java code, but I advise you to try programming this on your own to get a better grasp of the concepts. This pretty much sums up the solution covering problem 1696 on LeetCode. I hope this video has proven helpful in solving this problem. Thanks for watching.